I'm sorry. So hello everyone. My name is Misu Kim from Sungkyunkwan University. I'll be a moderator for the second part of this afternoon session. So we are going to have two distinguished invited speakers, Professor Andrew Mannix and Professor Jamie Pack, and two young scientists. And I'm looking for these talks. And our first distinguished speaker, invited speaker, is Professor Andrew Mannix from Stanford University. So, hi, Professor Andy Mannix. Would you want to turn on your, yes. Okay, so would you want to share your screen so that we can prepare for your talk? And meanwhile, I'd like to introduce your bio. So Professor Andrew Mannix is an assistant professor of materials science and engineering at Stanford University. He completed his BS in materials science and engineering at the University of Illinois at Urbana-Champaign, and his PhD as well in materials science and engineering at Northwestern University as an NSF GRFP fellow, where he worked on the growth and atomic scale characterization of new 2D materials. Before moving to Stanford, Andy was a Rice postdoctoral fellow in the James Franck Institute at the University of Chicago, where he developed new methods of atomically thin nanomaterials growth, processing, and automated heterostructure assembly. So he's going to share his amazing research topics with the title of Robotic 4-Dimensional Pixel Assembly of van der Waals solids. So the stage is yours. Thank you very much.
Excellent. Thank you so much for that kind introduction. And thank you, everyone. Can you all hear me okay?
Yeah, very clearly.
Excellent. Excellent. Thank you so much. Well, good afternoon, everyone. It's a distinct honor and a pleasure to have the opportunity to present my work to you all today. I'm going to be telling you about some work that I did as a postdoc at the University of Chicago that will be carrying forward in my lab at Stanford in new and exciting ways, because we believe that this is a technique that empowers us to explore the full potential of two-dimensional materials as a platform for atomic scale engineering. And what I'll be telling you about today is a robotic method of assembling two-dimensional materials into heterostructures. But before we get into that, it is of course important to motivate the purpose of work. And indeed, as material scientists, and that, of course, as you just heard, is my training, I'm very fascinated by this question of how can we control matter at the atomic scale? And if you attempt to do this within the classical limits imposed by sort of conventional three-dimensional crystals, you see that you suffer from a lot of different constraints. Among these, the fact that you have to match the lattices of different materials, that you have to deal with the potential for chemical interactions at interface due to the dangling bonds, and finally, that there's often very different thermal limits to what different materials can withstand. And all of this together makes it very hard to grow one material on top of another in a very generalizable fashion. So usually such epitaxy is limited to distinct families of materials. Furthermore, there's often a very strong trade-off that one has to make between the scalability of a technique versus the precision that you can achieve. So shown on the left is a cross-sectional TEM image of a relatively modern FinFET transistor. And you can see that it includes atomic scale features in terms of the gate oxide thickness, but nevertheless, the precision by which you can place these interfaces is maybe on the nanometer scale at best. And you don't get to control the discrete atomic arrangement between these different layers. In contrast, you can use very sophisticated techniques like this image shown on the right, which is a sequence of images obtained from a scanning tunneling microscope in ultra-high vacuum at 4 Kelvin. And it's shown here assembling a series of add atoms into a quantum chorale. So this is that very famous original STM quantum chorale result performed by Mike Cromie and others at IBM back in the 90s. And so, you know, this beautiful result demonstrates some excellent fundamental physics, but clearly these samples do not survive in air. They require ultra vacuum and they require low temperatures. And very exciting in the field of two-dimensional materials today is the fact that recognize the ability to stack these materials up into heterogeneous solids where we obtain angstrom scale control over the vertical composition by virtue of the atomically thin nature of these individual layers. And meanwhile, the lateral scale is dictated most ability to pattern them. And as the modern silicon semiconductor industry has shown, we can pattern things down to the nanometer scale, laterally speaking. So this provides a very powerful and complete tool set to engineer matter at the fundamental atomic limits in the vertical direction and the nanoscale limits in the lateral direction. And fortunately for us, two-dimensional materials include a wide variety of excellent properties to choose from. So not only can we pattern things very small, but we can make them exceptional in terms of their physical characteristics. Of course, this all started with graphene, an extremely strong semi-metal that has very high charge carrier mobilities, and hexagonal boron nitride, a very low disorder dielectric, and the transition metal dichalcogenides, a number of exceptional semiconductors, but there's a wider family of two-dimensional materials out there, and they all have their unique attributes, many of which are very exotic and interesting and may enable fundamentally new directions for future electronics, as well as some really cool fundamental physics. And so the idea that we like to explore is whether or not we these different materials, which we have, various classes to choose from, and we can assemble them into discrete stacks where we choose the thickness of each layer. And we can, right now use this to make individual devices. And that's largely where the field of two-dimensional materials is. But there's this great hope that we can scale this technique even further and we can make fully integrated circuits using two-dimensional materials. It's a challenging goal, but it's a goal that I hope that one day we can achieve. Furthermore, I hope that we can take advantage of some of the unique properties of two-dimensional materials, such as the fact that because you're layering these materials artificially on top of one another, you have control over the interlayer twist angle. And this interlayer twist angle gives us a lot of unique opportunities because now we can do two really cool things. We can offset the band structure of these materials in momentum space with respect to one another, which allows us to control the allowed electronic transitions. And we can also, by the overlap of the atomic periodicities, create the so-called Moire superlattice, which produces an array of quantum dots that is tunable in size. So these two phenomena together allow us to do a lot by just twisting these sheets. And so right now, these capabilities are very achievable today in the laboratory. And you see that there are many high-impact papers published every day that demonstrate the phenomena. But the beauty of these physics is overshadowed by the challenge in fabricating devices in these, because right now it is very, very common still to use Scotch tape exfoliated micromechanical flakes. These flakes have excellent quality. The crystalline quality is quite good. And so, the production is relatively inexpensive. And so because of this, it remains a premier technique. But nevertheless, you can see by looking at this image here that the flakes are very random in size and thickness and placement, and their crystalline orientation varies as well. And thus, it's very hard to use these as a platform for engineering. So, but nevertheless, researchers have been very innovative in using polymer stamps to go in and pick up these flakes one by one and use them to construct beautiful small-scale devices that reveal excellent physical properties. But if you try to do this with a lot of layers, then what you see rapidly is that the random shape of these flakes makes it very, very challenging to deterministically layer them on top of one another. And thus, what we would like to have is a technique that allows us to harness the beautiful layering capability of two-dimensional materials, but allows us to do this at large scale and control the shape and the exact thickness of all these layers as we put them together. And so that is what my work is striving towards right now, is trying to find ways to manufacture atomically engineered materials using two-dimensional building blocks. And in order to do this, we have to seek to control 4 distinct dimensions. First of all, we need to control the X and the Y dimensions. And this is sort of the lateral dimensions, which we can tailor both by shaping the individual layers. So lithographically speaking, we can structure them. And then we also need to be able to control their relative lateral alignment with respect to one another. Furthermore, we'd like to be able to control the vertical composition. This means that we need to be able to choose in which order we stack the sheets. This is something that the field is already quite good at, the second point. And finally, we'd like to be able to control this twist angle. And in particular, we'd like to be able to add arbitrarily many twist-controlled layers, which is something that currently cannot be done for reasons that I'll elaborate on later. So our proposal is that we can achieve this using current state-of-the-art technology by first growing our material at large wafer scale using high-quality chemical vapor deposition techniques. We can then pattern this material in an extremely clean way that avoids the formation of surface residues. And then we can assemble these using a robotic platform that allows us to rapidly put them together into very high quality heterostructures. And so taking a bunch of different materials that we have available to us, we were able to produce a wide variety of heterostructures with different characteristics. And so I'll be talking about how we did this today and how we can push this technique forward in the future. Basically, we start with this high quality MOCVD growth that my colleagues who are now at the University of Chicago demonstrated. And so basically, they focused on growing transition metal dichalcogenides using MOCVD. So they have a tube furnace-based reactor with various mass flow controllers and precursors, and they're able to demonstrate growth at the 4-inch wafer scale. And not only that, but they revealed that the interlayer adhesion between the two-dimensional layer and the underlying substrate is quite weak. So it's very easy to actually peel this off. It's great because we can use this material to people demonstrate Scotch tape material. So excellent temperatures. So this a few years ago by taking chips of MOCVD ground metal, peeling one layer off and pressing it against the next layer inside a vacuum chamber. And so you vacuum chamber achieve very smooth conformal interfaces between the two layers, and thus they adhere to one another with very nice van der Waals bonding. So you can then peel that layer off, and when you peel it, you bring not just the first layer but also the second layer as well. And so you can build up these stacks by successively pressing and peeling with a new source chip being placed in the chamber each time. And when you're done, you can then release this onto an arbitrary substrate. So they showed that you could do this at the wafer scale and that you could get much improved interfaces by doing this in vacuum. When you do this in air, there's a lot of trapped adsorbates and gases that get interface between the two materials, but just by going to a relatively low vacuum on the order of a few millibar, one is able to reduce this phenomena substantially and produce much higher quality interfaces at a large scale. And so they've demonstrated that this is very readily achievable to make complicated stacks at the centimeter scale. But what we would like to do is develop a technique that allows us to rapidly prototype devices using a large number of layers, because right now you would consume your entire wafer that you grew in order to produce such heterostructure. So we would like something intermediate scale, something that combines the versatility that research labs seek to have in terms of producing lots of distinctive devices, but at the same time, we want to be able to deterministically produce the source material for these devices. And so we like to start with our large scale growth, but we like to pattern it into smaller units that we can use in order to make a large number of distinct devices. And so this means that we have to take our source material and we have to pattern it into tiny individual units. And so we first start with our MOCVD growth, and then we use a novel patterning technique that has an adhesive template. And this adhesive template has small cavities embedded within it. So when you press this against the two-dimensional substrate, what you see is that you are actually not touching the two-dimensional material in certain areas. And so when you then peel this adhesive template away, it sticks very strongly to the two-dimensional material in the areas where it's in contact. But areas where it doesn't touch, actually leaves it and leave it on the surface. And so you turned template stripping approach, we're able to produce large chip scale patterns of very uniform and very high quality materials that have very little contamination because you never touch the surface of the two-dimensional material. So unlike conventional photolithography, this is a very easy to do technique that ultimately produces very clean interfaces, something that we found was a problem when we tried to use conventional clean room lithography with our materials. Now, with that said, I will admit that clean room lithography currently can achieve better resolution in this technique, but we still hope that we can use this to produce very interesting devices that we can explore the physics of two-dimensional materials with. Okay, so now once we have our chips that have a variety of patterned two-dimensional pixels, as we call them, we load these into our vacuum chamber. And we then use a series of micro positioners in order to pick up these individual two-dimensional materials by one. This is what our vacuum chamber looks like. It's a small modular vacuum chamber. It has a base pressure on the order of 10 to the minus 6 torr. And so this is a very convenient and modular platform that allowed us to test our ideas. And we have a small zoom microscope mounted here that allows us to observe our process as we're stacking up our material. You can see here that we have our stamp that allows us to go in and pick up these little pixels one at a time. And so you can see in this image here, we have the pillar of the stamp. We have our underlying substrate here, which is silicon with a thin film of thermal oxide on it, and it appears kind of purple. And then we have our individual layer. In this case, it's tungsten sulfide, shown as this little square pixel here. And so these stamps that we use to actually pick up the layers are very important because it allows us to target these layers one by one. And so we actually produce these using SU8 based lithography micromolding in the clean room. And so we pattern our PDMS using this SU8 mold. And so we get an array of these pillars. And then we spin coat a variety of different polymers on top of the PDMS in order to make it possible to program the adhesion and the interactions with the 2D materials. So we have first a rigid layer with a very large glass transition temperature. We have a release layer that can be disappeared by applying a thermal stimulus. And then finally, we have an adhesion layer that sticks very nicely to the two-dimensional materials. And so after we stack our materials and pick them up on this adhesion layer, we're able to then make the release layer disappear by applying excess heat. And when that release layer disappears, then it just drops off the adhesion layer film that has two-dimensional material stacked. So using our vacuum chamber-based automated assembly approach, then we're able to build up our heterostructures. And one really nice thing about our tech is because we have this small pillar on top, we're able to optically detect when we contact. And so we were able to avoid applying excess force because we can just program our computer to watch for this change in color at the interface. And that's a very simple algorithm. Basically, what we do is we navigate our stamp around on the surface. We find a region that we want to pick up. And because we've patterned these chips in a very regular array, we can actually program this in as a recipe. So we can give our computer a set of coordinates that it travels to on this grid. It will go to that location. It will press the stamp into that location, and then it will lift up the two-dimensional material. And when we've picked up enough layers on the stamp that we've completed our heterostructure, we then increase the sample stage temperature. We navigate to the final position, and we press it into contact and drop off the two-dimensional material stack. And so here is a video that actually shows this process in motion. This is us constructing a 16-layer heterostructure that systematically varies the thickness between 1 and 16 layers so that we can use this for optical testing for high throughput characterization. And this has actually been sped up by a factor of 100, but still this process completed in about 40 minutes to complete the 16-layer heterostructure. And in principle, it could speed up even faster, perhaps by a factor of 2 better than that at least. And so if you weren't able to see the issues, here's a series of still images taken when the stamp is in contact with the substrate. So you can see here that we've added 1 layer of MOS2, and then a unit that adds another set of layers. And these are basically like little Tetris block shaped pieces. And so by the end of the process now, we have a stack that varies from 1 to 16 layers that we can now explore the optical characteristics of this after we've removed the solvent, or we've used solvent to remove the polymer residue. And so here's that same heterostructure shown here, and we can use TEM to verify that the thickness is as expected based upon the design of our heterostructure. And we can also use optical techniques to characterize the properties of our film. And so we can actually use a hyperspectral spatially resolved wide field imaging technique where we basically vary the energy or the wavelength of the incident light, and we take either transmission or reflection images. And so using this, then we can quantify the absorbance of our two-dimensional stacks as a function of layer thickness. This is something that's very hard to do systematically for a wide variety of heterostructures. Normally, you're just limited to what you find via exfoliation. And so we can now look at the variation and the characteristics of our film from 1 to 17 layers in this case, because we can drop this stack off onto a uniform monolayer of MOS2. And this gives us an extra layer to look at. And so now we can then explore the various optical properties. We can see that the absorbance varies with layer count, and the PL varies, the photoluminescence varies with layer count as well. And we can actually plot these quantities together on the same plot based on curve fitting. And what we can see is that our absorbance converges to a value that resembles the bulk very quickly after only a few layers, whereas our photoluminescence values end up being very different from the bulk. Indeed, we converge at a sort of linear rate towards an equilibrium photoluminescence value that, although it's diminished from the monolayer, it doesn't diverge towards an exponentially small quantum efficiency, as you tend to see with the bulk material stacked in this sort of 2H crystal structure. So this is something that's still a little bit mysterious to us, but it is quite interesting that by using polycrystalline source MOCVD material, we can see a very different optical response by stacking it in this way. And this is something that we hope to generalize to a wider variety of two-dimensional materials. And one of the coolest things that we're very excited about is taking this technique and applying it towards these twist engineered structures. As was recently shown by Pablo Herrero Herrera's group at MIT, one can realize very exotic properties by twist engineering materials such as graphene. By stacking graphene at a magic angle, one can achieve unconventional superconductivity in this material. And so this is something that's very fascinating to us. And all of this work to date has been done by using material that has been exfoliated from, or that has been stacked from single exfoliated flakes. And so these flakes have very small area, and this limits naturally the amount of layers that you can add to your stack. So we're very excited about the property of being able to grow very large thin films of two-dimensional materials, and then being able to stack arbitrary numbers of layers with twist engineering. And so in principle, if we can grow an entire chip of epitaxial material, we hope to be able to produce arbitrarily thick, many layer rotational superlattices, where we can engineer the interactions between many different layers in our stack, not just one pair of adjacent layers. And this allows us to explore a lot of really cool phenomena. For instance, right now it is known that in twisted bilayer graphene, you can see a reconstruction. So if you just take these two layers and put them on top of one another, you would expect initially at first glance that you would have regions that have continuous variation in the stacking alignment between the two layers based on this moire pattern. But what one actually sees for small angles is that there's a reconstruction. So the lattices of the two graphene layers actually shift in order to form these energetically preferred configurations. And so this excellent work from Philip Pim's group showed systematically that you can vary the angle between these layers, and you can see variation in terms of the resultant moire pattern and in terms of the lattice reconstruction. And this lattice reconstruction is obvious because of the TEM diffraction patterns shown here. And so, by the way, these are TEM dark field images up at the top here. And basically, the intensity of these diffraction spots gives us a hint as to the fact that this is a reconstructive process. And this is similarly very important for twisted bilayers of transition metal dichalcogenides, where the magic angle phenomena spans a wide variety of different layers. And thus, we'd like to know what happens structurally between these layers as we stack them on top of one another. So this is something that has been explored a little bit to date in the literature using twisted bilayers, but there's an added degree of complexity because now our material has only threefold symmetry as opposed to the sixfold symmetry present in graphene. So we actually have to consider a wider variety of different angular configurations. And so anyway, this is something that we're very excited about. And so we decided to apply our robotic stacking technique towards this. So what we did is we optimized our MOCVD growth conditions to produce large triangles of, in this case, tungsten sulfide. And then we go in and we basically cut out little crystalline segments of this material by using our microstructured stamp. And so if we go in and we take our stamp and we remove little pieces of this material one at a time, we can actually produce very complex stacks, even though we have only these relatively small crystals, because these crystals are still much bigger than what one sees with exfoliated flakes. And so if we look at these in the TEM diffraction pattern, we see for one layer, we have this sort of hexagonal diffraction pattern. if we add a second layer, we see a number of other spots emerge. And in this case, because it's just a bare bilayer, we actually don't see any reconstruction, which was sort of disappointing. But what was really exciting to us is that when we went to a larger area or a larger angle and we added 4 layers, we actually saw this reconstruction reemerge. And this is something that we did not expect, because this is a very large angle to observe this kind of interlayer reconstruction. It's not expected at this large of an angle. And so what we believe is happening is that having more layers actually makes it easier for the layers to reconstruct. And so we can see from these different first, second, and third order diffraction spots that there are obvious superlattice peaks that emerge due to this reconstruction phenomenon. And if we put our objective aperture over the second order spots, we can actually observe this phenomenon in real space using dark field TEM. And so we can see here that we have this complex set of different superperiodicities emerge. We have this sort of rhombohedral pattern that is due to the nearest neighbor reconstruction, and we have this linear pattern that emerges due to next nearest neighbor and second next nearest neighbor interactions. And so this is something that we're still actively exploring. In other words, what is the nature of this complex many-layer reconstruction phenomenon? But we're very excited by the fact that it seems to enable reconstruction beyond the simple 2-layer reconstructive limit. And so with that, I'd like to conclude today by noting that we've achieved 4-dimensional control over the assembly of 2-dimensional materials, both in X and Y, in terms of vertical composition and in terms of interlayer rotation, using our van der Waals pixel assembly technique, which employs large-scale growth, clean patterning, and automated assembly. And this has allowed us to produce very complex heterostructured solids that have complicated internal geometry to produce many-layered twist engineering. And this is something that we've used to demonstrate new reconstructive phenomena. So with that, I'd like to thank everybody who made this work possible. First of all, my colleagues at the University of Chicago who made all this happen, as well as our collaborators at Cornell and the University of Michigan. And I'd also like to take this moment to sort of acknowledge my research group, which we're building up at Stanford, in order to explore these phenomena further by looking at the growth of new 2-dimensional materials, the characterization of materials via scanning tunneling microscopy, and the next generation of robotic heterostructure fabrication that we're building in ultra-high vacuum. And so we're currently actually recruiting for students and postdocs. So if this sounds fun and interesting to you, please feel free to reach out to me. So with that, I'd like to thank you all for your time today, and I'm happy to answer any questions that you have.
Thank you so much for your wonderful talk. The automated fabrication process is especially fascinating to me. So would there be any question or comments from the audience?
Yeah, I have one question.
Sure, go ahead.
Yeah, thank you, Professor, for such a wonderful talk. You have shown such an interesting transfer of layer by layer through vacuum stacking. But how about, I'm just curious about the defects or cracks formation during the transfer, because it shows some kind of curvature during the transfer of the stamp. So it may create some kind of cracks formation, maybe may not be in the nano level range, but maybe in the micron or maybe few millimeters range. So
yeah, that's an excellent question. And that's something we've been very concerned about. And to be honest, the building the robot was actually quite easy. It was the optimization of the material quality by polymer engineering that took forever. So we tried literally hundreds of different polymer combinations in order to arrive on the one that we found to be optimal. And the tri-layer structure of polymers that we spin coat on top of our PDMS is key to reducing this problem that you mentioned. So I actually have a couple slides that I can use to address this. I don't want to take too long because I don't know if there's other questions, but you can see in our variation from these 2 images that I showed here from 1 to 16 layers, that by the time you get to 16 layers, the quality is becoming a little bit less. These are still, by the way, very large areas if you were comparing them to exfoliated flakes. And this is a 100 by 100 micron square region, which is large enough to make maybe a few devices in. If we go to 25 layers, we see that the quality is still okay. But if we get to 80 layers, we see now that there are very obvious wrinkles there. And this is something that we are not very happy about. And we've identified the source of this wrinkling. So basically, we can keep adding layers to the stack, and there's no problem there because the bottom remains very smooth. But the differential thermal expansion and contraction of the polymer is a real issue. So in our next generation tool, we've actually created an isothermal stage that has both the stamp and the sample at the exact same temperature. And this should avoid this thermal cycling problem. And so that's one way to address this. But nevertheless, I will also show some images of thicker films that we've picked up. And you can see here that although maybe near the edges, there's a little bit of wrinkling in some cases due to the uneven initial contact, what we found is that the films overall survive pretty well. And so again, this is something that I think if we can achieve perfect coplanarity between the two surfaces via active in situ measurement, that we should be able to resolve this issue. So yeah, I think you're totally right. I think this is something that we're really acutely aware of and we hope to solve in the future.
Yeah, thank you, Professor. Yeah.
Okay, any other question from the audience?
Yes, I have a question to ask. Hello?
Okay, go
hello.
ahead, Dr. Pavan.
Yeah. As far as this 2D heterostructures are concerned, the physics is very rich at the interface. So my question is it possible to maintain a customized atomic sequence in the stacked heterostructure with this technique? Because as far as what I see from your slides is more of in a micro level. So if I want to have a proper atomic sequence between the layers, so is it possible to have with this technique?
Okay, so I want to make sure I understand the question fully. So do you mean that we control the vertical composition at the atomic scale in a sense because we have the ordering of the two-dimensional layers that we're maintaining. But
Yeah.
if you mean in terms of the exact lateral registry between atoms, that's something that we cannot actively control at the moment. Is that what you meant?
Yeah. Because the atomic sequence, suppose if I want to have heterostructure between two different kind of 2D layers, and what is there on one above the other in terms of atomic scale, that makes more like the study of physics will be much more. I feel the physics is very rich at the interface. So what I feel is that. So one time.
Yeah. Please go ahead. I'm sorry.
Yeah, the thing is, suppose say I have when it comes to reproducibility, suppose say one time I do I go with a heterostructure where the atomic sequence is different from another stacking. Suppose if I have say AB sequence, in the next time when I do the same experiment, so I may not get the same atomic sequence. So the physics changes from one person to another. Like, what I feel is that this is just my view.
Sure. Okay. Yeah. So what I can say is that this is something that so far nobody can precisely control within this field, but nevertheless, we find that the general characteristics of devices, say for instance, twisted bilayer graphene at the magic angle, displays, the same essential physics from group to group. It's been reproduced across the world and in many, many devices. But what's fascinating but also challenging about this field is that the precise physics often does vary from device to device, but we think that this is not necessarily due to variation in, let's say, the exact lateral registry between atoms, but it's more like, for instance, disorder in the twist angle across the device. And so this is something that we are seeking to actively control or to improve our quality. We want to actually benchmark that using this technique. So I think you're right in the sense that it would be extremely challenging to deterministically control the interlayer registry between every single atom. But I think that the essential physics is captured merely by the angle of rotation and the vertical sequence of stacking. And there will be some energetic relaxation into minima between the layers if this reconstructive phenomenon happens as well. So I hope I maybe was able to answer your question or at least address your comments. I think.
Yeah. Thank you, Professor.
Okay, so since we are a little bit behind the schedule, so I have to let Professor Andy Mannix go. Thank you so much for your wonderful talk and the questions and answers. Thank you very much. Hope to see you again soon. And we'd like to move on to the next talk. The next speaker is Ji-hyun Kim from Sungkyunkwan University. So if the presenter is ready, would you want to share the screen? Okay, so the title of the talk is, you're looking at it, so I wouldn't introduce it. So just please go ahead. It looks good. Do we have our presenter here? I'm sorry, I cannot see her name here.
Sorry.
Do we have our presenter, Jihyun Kim?
Yes, I'm here.
Oh, okay. Would you want to start your presentation?
Okay. Hi, everyone. My name is Jihyun Kim. I'm a PhD candidate in the Department of Material Science and Engineering. Today, I'm going to present my research, which focus on multifunction device, which focus on multifunction device by modulating the interface based on solution processing. Because of diverse and unique properties, graphene and related two-dimensional materials are considered as a material platform for next generation optoelectronics. In particular, the difference in electrical property depending on the material shows the potential for diverse device application, such as tunneling transistor, resonant tunneling diode, light emitting diode, and so on. In this system, important consideration is that material with few layers lead to exotic properties that do not exist in bulk form. So it inevitably leads to the following question: how to obtain few layer 2D material effectively? To obtain 2D material effectively, a number of material production methods have been developed over the last decade. An important part of the research has been devoted to the development of cost-effective and mass production methods. Although high-quality 2D samples are prepared by mechanical exfoliation or chemical vapor deposition, the resulting samples only have been used to demonstrate optoelectronic and electronic applications, prototype optoelectronics. So, to translate fundamental study to real-world application, our approach is solution processing. Solution processing has been considered as a photosynthesis route for scalable production with low cost. This method generally relies on the exfoliation of bulk crystal in specific solvent by the mechanical energy transfer that overcome the van der Waals interaction within layered material. It is a simple way for preparing high concentration 2D dispersion. High throughput achieved by solution processing promotes the large area thin film application enabled by various deposition techniques such as vacuum filtration, spray coating, inkjet printing, drop casting, and so on. Although solution processing provides the best trade-off between yield and cost, it has some limitations. Because underlying mechanism in liquid phase exfoliation is high power vibration and cavitation forces, it results in small lateral sized nanoflakes. As you can see above, morphology of exfoliated nanoflakes is close to nanoparticle even after the centrifuge processing. Also, this exfoliated nanoflakes shows broad size distribution. So, when exfoliated nanoflakes are assembled into film network structure, non-conformal contacts are formed between nanoflakes. This results in an enormous number of contact resistance and poor interflake connectivity. As a result, solution processed MOS to thin film device cannot fully duplicate the intrinsic property of MOS2 discovered from mechanical exfoliated high-quality sample. It is a major bottleneck in the development of solution process thin film optoelectronics. So, interface issues must be improved. To further gain an understanding of interface, we compare the contact within a film according to the morphology of 2D material. A thin film with large aspect ratio nanoflakes can form clean interface, which means free of disordered chemical bonding. This makes low energy barrier between nanoflakes, implying the formation of low contact resistance device. On the other hand, thin film with small aspect ratio nanoflakes feature a large number of grain boundaries due to their nanometer scale size. These grain boundaries can act as transport barrier and charge trapping sites, which seriously degrade the transport properties. To overcome the conventional limitation discussed above, we developed a fossil synthesis route for MOS2 thin film with chalcogen vacancy induced functional interface for improving the contact resistance, and we call it chemical welding. In this method, subsequent annealing of thin film results in converting the precursor to defective MOS2-X at interface, which can act as conductive pathway. This chemically welded MOS2 thin film device exhibits 2-order higher electrical conductivity than that of the pristine. This increased electrical conductivity can be explained with defective MOS2-X at interface. Furthermore, we demonstrate the origin of high electrical conductivity by XPS analysis, where MO6+ ratio can provide the evidence of degree of oxidation. Similar level of MO6+ ratio before and after the treatment means that increased electrical conductivity is not originated from the formation of metallic MO3. Enhanced charge transport further motivate the application in thin film photodetector. First, chemically welded film is characterized its detection property at 532 nanometer green laser. IV measurement and time-dependent plot before and after the exposure shows photoresponse. Also, in the view of photoresponsivity, which is the indicator of the performance of photodetector, this welded film shows high value among the solution process TMD-based thin film photodetector. Also, unlike pristine MOS2 flake, defective MOS2-X possesses defect-induced energy state within energy band, which can make NIR range absorption possible. To examine the photoresponse under NIR range, we perform the photodetection measurement under 1060 nanometer laser. This chemically welded film shows photoresponse under NIR range. Also, time-dependent plot shows clear absorption contrast between welded film and pristine film. Because this wavelength is out of pristine MOS2 cutoff wavelengths, this photoresponse can be explained with defect-induced functional interface. Based on previous photodetection characteristic, we further fabricate 6x6 array device to examine uniformity and regularity of the device. Our chemical welded film shows clear photoresponse in red, green, blue, and NIR range light. Also, based on two-dimensional mapping based on photocurrent, shows uniformity of the device. This shows applicability for large area NIR range, applicability for large area broadband image sensor. Another approach for chemical welding is additive for hydrogen evolution reaction. It is widely known that etch site or sulfur vacancy can act as active site for hydrogen evolution. Based on current density curve, this welded film shows improved overpotential. Also, Nyquist plot of chemical welded film shows low charge transport resistance than other control samples. This shows this chemical welding method can promote performance of catalyst. This is the end of my presentation. Today, I present proper processing with scalable production of materials by solution processing for next optoelectronics. And our multifunction method can improve contact resistance and detection range through defect-induced interface. Also, welded film shows high photoresponse at red, green, blue, and NIR range light. Last, our method can applicable for additive for catalyst. Thank you for your listening.
Thank you very much for your interesting talk. So any question or comment from the audience for the speaker?
Hello, I have one question.
Yeah, go ahead.
Yeah, I want to ask what is the band gap of this welded MOS2 so that
Pardon?
it can detect NIR range?
Sorry, can I hear
yeah,
one
yeah.
more time?
Yeah, there must be some band gap change for
Yes.
your welded MOS2
Yes, yes.
so that it can detect the NIR range.
Yes.
So can I know that what is the change in the band gap?
Unlike pristine MOS2 flake, defective MOS2 minus X possess defect-induced energy state within intrinsic band gap. So it can absorb low energy wavelength light than pristine MOS2 flake.
Oh, it means you have introduced some more states in between CV and PB.
Yeah.
Okay. Okay, thank you.
Oh, thank you.
Okay, very good. So we'd like to wrap up at this point so that we can move on. Thank you very much, Ji-hyun Kim. So our next distinguished speaker for the invited talk is Professor, we're going to have Professor Jamie Peck from EPFL. And hello.
Morning or afternoon.
Yeah, good afternoon here. So good to see you here. So would you like to share your screen so that I can introduce you during while? So Professor Jamie Peck